Okay. All right, we're going to simplify radicals because when we come back from Thanksgiving break, we're going to talk about a process called completing the square, which should make you think, yes, we're going to start doing stuff with square roots. So what we have to do is remember, we made a list the other day of all those nice little perfect squares. 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared is 25, 6 squared is 36, etc. And when we say simplifying square roots, we're not talking about just making them look simpler. Simplifying square roots means you have to take out any perfect squares that are factors, and you can never leave a radical in the denominator. So if we looked it up in the dictionary, simplifying square roots, it would not say making them look nicer. That's not what it is. It's taking out pieces that we understand we can use. So when we have the square root of 50, we're supposed to go through this list kind of mentally and find the biggest one out of those perfect squares that would divide nicely into 50. It's 25. So we write it as the square root of 25 times the square root of 2 because 2 square roots can be multiplied together, and this has to work forwards and backwards. So square root of 25 times the square root of 2 is definitely the square root of 50. And then we say, but wait a minute, we picked this one for a reason, because it's nice. I know what the square root of 25 is, it's 5. So we write it as 5. And even though people would argue, I think that one looks simpler than this one, this is really the simplified form right here. This is our answer, because we took out those perfect square factors. B. A little bit different. You know, it's working with radicals, but then we see that it says squared. Well, remember that powers go to the closest thing to them on their left. So this would be one way to do the problem, where you go, hey, I'm going to have to write that down twice. And then you realize, okay, I can take the integer times the integer. 3 times 3 is 9. I'm just going to stop for a second, so those of you that have your phones and are sitting there pushing buttons like crazy, can just put those away, because I already promised you this was only going to take 10 minutes, for goodness sake. Give me 10 minutes of your time. And then the square root of 17 times the square root of 17, well, we could always take 17 times 17 if we want to, and get 289. But it's going to be the square root of 289, because it's the square root of 17 and the square root of 17. And then we go, wait a minute, square root of 289 is 17. So my answer is just going to be 9 times 17. There it is. Now that's one way to do that problem. Let me show you the other way. The other way is by looking at the 3 square roots of 17 squared and saying to yourself, self, I think when there's no pluses or minuses in there, I can distribute that power. And you can't. If it's pure multiplication or division, we can distribute this power. So that would make it 3 squared times the square root of 17 squared. Well, 3 squared is 9. And then you remember square roots and squaring. Aren't those like inverses of each other? Don't they cancel each other out? And they do. We'll still get the same answer. It's just a different way of doing it, you know? So to meet our objective today, which is just simplifying square roots, it wouldn't matter which one of those you do. And you might say, well, this one took one less step. I'm going to use the green one instead of the blue one, you know, but it makes no difference. Do remember, though, if there's addition or subtraction inside these parentheses, we can't do that. We cannot distribute that too. Alrighty, down here. Square root of 5/11ths. First thing to do would be to ask yourself, can I reduce 5/11ths? Rats. All right, can't reduce 5/11ths. Okay, so I know I can write it like this. And then I ask myself, well, does that help? You know, splitting that up. No, it didn't help me either. But you know, it makes me realize that the square root of 5 on the top, I couldn't care less about that. That can be there, but I just can't leave that square root of 11 down there. So then I think about what we just did in the last problem, where we had that. And we were able to get rid of the square root and the squaring and just say, hey, that's 17. And I think, well, I could get rid of the square root thing if I just make it the square root of 11 squared. And that means I'd have to multiply the top and the bottom by the square root of 11 to get that. On the top, they're both square roots. So 5 times 11 is 55. Square root of 55 on the top. But on the bottom, I now have the square root of 11 squared. And that's going to give me 11 back. And then I say to myself, self, are there any nice perfect squares that are going to divide into 55 nicely? There's nothing on that list over there that we had of the 4, 9, 16, 25, 36. Oh, I had to erase it to do the green part there. None of that's going to go in there. So that one's done. Nothing else we can do with that. Square root of 55 over 11. D. Square root of 300. Now the negative part, that's just going to come along for the ride. There's nothing we can do about that. If it's under the radical, then we can't do this problem. Because watch what happens if I ask my calculator to take the square root of negative 100. It yells at me. It's not a real answer. You can't do that. There aren't two numbers that you can multiply the same number of times itself and it'll give you something negative. They either have to both be positive or both be negative, and in either case they're going to give you something that's positive. So negative rides along. And now I'm thinking about my list of perfect squares. Can you think of a large perfect square that'll divide into 300 nicely? 100. And it goes in there 3 times. So then you say, well, why did I pick 100? Because it's nice. Because when I take the square root of 100, I get 10. And sometimes people will ask, when do you know to drop the square root? Did you do some math? To think through this square root of 100 to get the 10, you had to do some math. You had to think, okay, what is square root? What does that do? And that's the answer. Then E. Square root of 12 over x squared. First thing you ask yourself is, can I reduce that? No. There's nothing in the top that's going to cancel at the bottom. So my next step would be, how about if I split it? Does that help me out at all? It did. So what did I just get in my denominator by splitting that? X. Remember, these are inverses of each other. Square root of 12. We have a perfect square that goes into 12 nicely. 4. So that'll be 2 square roots of 3 over x. But here's the problem. We're not done. We think we are. I mean, we look at that and we go, hey, that's nice and simple. I took all the perfect squares out. Everything's great. But there's always an issue when you talk about square roots of variables, and here's why. When the person wrote this problem, you could put negatives in here, positives in here. It didn't matter. You were going to square it, and everything was going to be positive. And then you could punch it in your calculator, and voila, you would get an answer. But there's never any chance that you're going to get a negative because your variable always had to be squared. If we simplified this, did not give people that formula, and tell them they can put whatever x they want in this, is there a possibility that it would then be negative? Of course there is. Because if somebody puts negative 5 in here, this answer's coming out negative. That's not what the person that wrote the problem wanted. So what we have to do is slap a couple of absolute value bars on that x. We have to do that. Now, if you want an easy way to remember when you have to do that, if you have an even root, so you look up here and you realize that's a square root, so that's a little 2. And when you get done, you have an odd power answer. This is x to the first, and 1 is odd. You need absolute value bars. So that's the shortcut. Let's write the shortcut down. Even roots that have odd variable, I should say odd power variable answers. Even roots that have odd power variable answers need absolute value. So for your assignment, you can kind of go through, do all the problems, and then go back and say to yourself, okay, if these were all square roots, if any of my answers came out to x to the first, x to the third, x to the fifth, x to the seventh, I've got to slap some absolute value bars on. So that's the shortcut to remembering that. Let's look at this little bugger right here. Come on back. I think we can do some canceling on that one. Because on the top we have x to the 5th. That's x times x times x times x times x. And on the bottom we have x to the 3rd. X times x times x. Well, we cancel. Cancel 3 of them off. We have 2 of them left. So this will be negative square root of 3x squared over 2. So already we've made it simpler. Now if you're thinking, okay, Cedar, that really was the wrong way, because I remember we learned a real shortcut in exponential, and in exponential they told us when you divide you subtract the exponents for similar bases. If you remembered that, fantastic for you. But it's been so long, I think some people may have forgotten those properties. So now I have this mess. Well, let me separate it and see if that's helpful. Okay, well that didn't really help, but how about if I separate these two up here? And get everything all separated. Is any of that nice? Which one? Yeah, the square root of x squared is x. So we'll get negative x square roots of 3 over the square root of 2. I just put the x in front so it wasn't all awkward. But we're not done, because we still have a radical in the denominator. Do you remember what to do from the one that we had that had rationalizing the denominator, it's called? Multiply top and bottom, square root of 2. So negative x square roots of 6, because remember, square roots can only get multiplied by other square roots. But on the bottom, you can either think of it as the square root of 4, which is 2, or the square root of 2 squared, which is 2. And there it is. And we know we're done because the square root of 6, we don't have any perfect squares. That would go into that. So then, does this need absolute value bars? Did we take an even root? Is this x an odd power? We need absolute value bars. So it's going to be the negative absolute value of x, square roots of 6 over 2. We've got it. Even root, odd power answer. Slap the absolute value on. Simplify square roots. 4, 3, 2, 1, 0 me. How are you feeling? Coming back a little bit. Yeah, see, they're coming back a little. Some people more confident than others. All right, well, that's what this is for, and that's what this time is for. Oh, and ignore this. Obviously, it's not tomorrow, but you guys can finish this before you go. For goodness sake, you got until 12:10. You know?